Hi everyone, welcome back to the session. I would like to introduce our first speaker for this part of the session. So our first speaker is Alistair Duffey, who's a soon-to-be PhD in climate science at the University College London. His research uses Earth system models to simulate the climate impacts of SAI, with a focus on the Arctic region and scenarios of low-altitude polar deployments. Also, as a scientist at the non-profit Reflective, Alistair leads work on developing data infrastructure to support the SRM research community. So please welcome Alistair.
Thanks, Matthew. Hi, everyone. Cool. My name is Alistair Duffey. As Matthew said, I'm a PhD student at University College London, hopefully finishing soon. I'm going to talk today about the Arctic energy budget under stratospheric aerosol injection, or more broadly, what we think will happen to the Arctic under global SAI scenarios and why. That's the aim here. And I should say thank you before I carry on to Matthew Henry, to Pete Irvin, to Michelle Samados, to many of us who've worked with me on this project, to Matthew in particular for running the simulations that I'll be showing. Cool. There's two reasons that I think it's important to consider SAI in the Arctic context. So one of those reasons is that Arctic deployment might be easier. And Wakesmith talked about that this morning. I have a paper on that from earlier this year that I'd love people to check out. But the second reason, and what I'll talk about today, is that reducing Arctic climate change might be the aim of your deployments, right? Everyone at this conference understands why that could be a target, right? And so as a first thing to note, and I think it's really important to note this first, whenever we do kind of science talks on SAI, is that the leading order effect is that SAI works, right? Like every single model shows something that looks a bit like this, that if you do enough SAI, you cool the planet, you cool the Arctic, you get more sea ice. And you know, I often like to show this GIF, partly because it took me a long time to learn how to make GIFs, but also because I think it's important to stress that before we delve into the detailed science, because you know, most of the work that we do is often looking at these kind of, you know, the residual effects relative to the target, for example, the smaller effects where a lot of the scientific interest is. But this first order effect, you know, is an important thing to note before we do that. The SAI would cool the Arctic, and many Arctic responses are broadly temperature driven, as Pete mentioned this morning, and so respond, as you might expect, with, for example, more sea ice. Cool. But certainly globally uniform SAI would undercool the Arctic. This is a result that goes back a long way. It was something that some of the earliest modeling papers on SAI noted. People like Bala Govindasamy. This is a figure from Ben Kravitz, who had a paper in 2013 that showed the same effect. You know, if you uniformly reflect sunlight, that tends to have this pattern of undercooling in the polar regions and overcooling in the tropics for a given global temperature. And the reason for that is somewhat intuitive. CO2 acts broadly everywhere, whereas there's more sunlight at the equator. And so if you cancel the two out, you have this net effect of some residual warming in the polar regions. And the figure, can I point? Oh. There we go. This figure is kind of showing you that in more quantitative detail. As you get towards the polar regions, you have more albedo, i.e. you have a more reflective surface and you have less insolation. And when you add those things together, what you find is that if you just if you reduce sunlight by say 1%, you're having something like 3 times less energy perturbation on a per meter squared basis in the Arctic. But this is all for a uniform reduction of sunlight. We can't do that, at least not in the near term. So how does the Arctic respond under more realistic scenarios of actually putting aerosols into the stratosphere? That's the question I'll try and answer with the next kind of set of slides. And to target this question, I'll be showing results from a set of simulations that were recently run in the UK Earth System Model by Matthew Henry. See the paper from last year if you want more detail on these simulations. Essentially, these are really nice because they all target the same thing. So we're always holding the global temperature to 1.5 degrees C, but they do it in different ways. So we have a set of simulations that inject at the equator, at 15 degrees north-south, at 30 degrees north-south, and at 60 degrees north-south, all setting their magnitude to hold the global mean temperature to 1.5 degrees C under a kind of moderate background scenario. moderate in the sense of not doing that much in the way of emissions reductions, right? So that word is a somewhat loaded term. But they then have very different styles of SAI. So if you then look at the right-hand figure, what you're seeing is the stratospheric aerosol optical depth, and you can kind of think of this as where the aerosols are on the planet. And this is going from the South Pole to the North Pole, and you see that if you inject near the equator, you have this big peak near the equator. As you then eject it further away from the equator, you kind of have the opposite effect. And by 60 degrees north-south injection, you're peaking at the two poles. And so I really like this set of simulations because we can essentially span that space of different styles of SAI to try and understand why they produce different outcomes. Okay. The first thing you'll note when you look at these kind of simulations is a result that's not new, but is borne out here quite well, which is that the further away from the Arctic you inject, the less Arctic cooling you get for a given global cooling. And so if we take the equatorial injection case here, the blue lines, what you see is that while they're cooling the globe close to their target state of 1.5 degrees C, the relevant Arctic state, which is nearly 4 degrees C, which is the Arctic temperature at that target world, is not met by the equatorial injection. But as you move towards injecting at higher latitudes, you get closer to meeting that Arctic target. And if we then look at that in a spatial picture, what you see is that what that means in practice is if you're injecting near the equator, you might have something like a 20 or 30% efficacy in the Arctic. And by efficacy here, I mean how much of this warming gap has been offset by the cooling from SAI in each kind of grid cell of the model. And so you see this kind of yellowish color here where you're saying actually for lots of the central Arctic, if you're injecting at the equator, you don't achieve that much local cooling. By contrast, as you inject more polar, you reverse this effect to some extent, and you get something like 100% efficacy, not quite, towards the polar regions, and actually you're peaking kind of in the mid-latitudes. Okay, and then just to sum up that statement in more detail, or more quantitatively, essentially as we move towards higher latitudes of injection, your ratio of Arctic to global temperature difference, the delta T Arctic, delta T global, is this kind of ratio of how much Arctic cooling you get for a global perturbation, increases, as you might expect. So more polar distributions of aerosols increase that ratio. They don't actually quite make it to this gray line, which is the warming ratio. This is the Arctic amplification ratio people often talk about. In this model, it's just a bit over 3. And kind of interestingly, even if you inject at 60 degrees at 22 kilometers, you don't quite cool the Arctic as much as it's warming under greenhouse gases relative to the world. This green and red cross, I won't talk too much about, but that actually shows that if you drop your altitude, you can start to beat that ratio. And so at this low altitude case, you do get these more polar, even more polar distributions of aerosols that can go above that line. But in a way, this is the kind of physicist's view of the thing. I also wanted to take the kind of maybe the more policy relevant view of the thing, which is if we instead plot this in terms of the delta T Arctic, i.e. the Arctic temperature change per unit of injection, this is how much gunk we're putting into the sky, as Wake would put it. If you plot it as per unit injection, you actually see something quite different. Essentially, the peak here is at lower latitude. And there's not a huge amount of variation by latitude at all, as long as you're getting away from the equator. So what that's telling us is that actually, if you're interested in the question, how could I cool the Arctic maximally for a given amount of stuff we put in the sky, more polar deployments are not necessarily more effective at Arctic cooling. And that kind of surprised me when I first plotted this, but if you think about it, it shouldn't necessarily surprise us, right? We maybe have a longer lifetime of aerosols at lower latitude. There's more insulation at lower latitude for those aerosols to reflect. And as a general rule, the planet doesn't like strong gradients of temperature. If you cool one place, then heat transports will oppose large gradients. And to delve into that in some more detail, I then took this energy budget approach, right? So we can think about an energy budget for the Arctic atmospheric column, and I've taken this figure from Jake Elmer's paper from last year, where we kind of just, essentially imagine a cylinder over the Arctic, and you've got heat transports into the sides of that cylinder, into the top and bottom of that cylinder, and that defines this energy budget for the atmospheric column. And doing that allows us to tease out differences between atmospheric heat transports, which are in blue here, versus solar absorption, so that the shortwave energy going in, the net SW here, the shortwave, and then that's balanced by long wave to space, these red columns. And then there's also some surface transports into the atmosphere from the surface. And so in the present day, you see what you kind of imagine in the summer months, which is in the middle here. The Arctic is dominated by shortwave radiation that comes in from the sun. But in the winter months, there's no sunlight, and you're getting a balance between atmospheric heat transports coming into the Arctic, balanced by long-wave radiation escaping to space. And then as we kind of warm the planet, this changes, and you can see this perturbation where essentially more long-wave to space is offset against some extra energy coming in. We can then use the same framework and apply it to our SAI scenarios. And what we see when we do that essentially is part of the explanation for how the differences between latitudinal strategies are perhaps not as large as one might imagine going in. And in particular, I draw your attention to these blue bars. So here the graphs are showing you equatorial injection through to, on the right, 60-degree north-south injection, so more polar SAI versus more equatorial SAI on the left. And as you pan across, what you see is that on this left-hand side, these blue bars are mostly negative. And so you're seeing that when you inject at the equator, you're cooling the Arctic in part, or in large part, by reducing the heat transport from the lower latitudes into the polar regions. You cool the lower latitudes, and your heat transport northward is getting lower. Whereas as we move towards a more polar injection scenario, the reverse happens. And actually, if you try and do enough cooling locally, the planet kind of fights back, and you're getting more poleward heat transport because you've got this localized cooling. And this isn't the whole story for the differences between these scenarios, but I think it's an important contributor to why you maybe don't see as much difference in terms of the Arctic cooling between these scenarios as you might imagine going in. These plots get a little bit complicated, so forgive me for that. But I think it's also important to stress, and this is maybe the last technical point I'll stress, we often assume that SAI doesn't work in the Arctic winter because there's no sunlight to reflect. That's kind of a thing you hear often, and it's not true, right? Like, this is the warming pattern over the seasons, and you see this characteristic winter-fall peak in warming in the Arctic. And these gray bars are the same in each case. These are different SAI scenarios, and this is the Arctic region's warming pattern. That's then opposed by a cooling pattern under SAI. And the first thing you'll notice is that essentially the shapes are consistent. Right? These all look a bit like TIE fighters from Star Wars. Essentially, they all peak in the winter months. And that's because fundamentally there are local drivers that force the Arctic change to peak in those months. And that's an important thing to remember. We're reflecting sunlight only in these summer months, but our cooling profile is peaking in the winter. If we take one extra kind of step of complication here and normalize these, so we're going to take these graphs here and then we divide by the total Arctic cooling, this tells you something like if you were to fully cool the Arctic to a particular target level, you set your magnitude of injections such the Arctic gets to a cooling level you've decided you want to get to, what's the residual seasonality? That's what these plots are showing you here. And so this equatorial case is showing you that if you were to use equatorial SAI to cool the Arctic to a particular target, what you find is that you actually overcool in the summer and you undercool in these shoulder seasons quite strongly. And so you have this characteristic kind of seasonality that's residual in your cooling. And then as we move towards more Arctic injections, that seasonality remains to some extent, particularly the summer overcooling and the spring undercooling. But this fall peak kind of goes away. If anyone has ideas for why that would be, come talk to me because I'm interested. But essentially what this is really showing you is that there is a certain amount of unavoidable seasonality in SAI. You can't get the Arctic perfect in its seasonal cooling because of the fact that you're reflecting sunlight and not reducing greenhouse gases. But the top layer is showing you that the first order effect is that you're cooling still peaks in the winter. Okay, so key points really. First, if you want to cool the Arctic maximally per unit of global cooling, i.e. for your global perturbation of the temperature, then you should be injecting at high latitudes. But that's not the same as saying that if you want to cool the Arctic maximally for a given amount of mass, you should be injecting at high latitudes. At least in this climate model, that doesn't seem to be the case. Part of the reason for why this maybe isn't as one might imagine is that actually the heat transport is really important here. You can't really affect the planet in just one place. You affect the whole planet and it responds. And then finally, there's a certain amount of seasonality built into using SAI, and it appears that none of these strategies fully prevent that seasonality remaining in these residuals. But the first order effect is that your cooling, as with the warming, peaks in the local winter. Cool. Cool. I've got 1 minute remaining, so I might just quickly go on to the other reason to consider SI in the Arctic context, which is that Arctic deployment might be easier. I'm just going to flag, look at Walker Lee's poster, which is outside, presenting some really exciting new simulations of these Hiller SAI, as we're calling it, high latitude, low altitude. I'm delighted to find out that Hiller also is finished for Cloudberry, apparently, according to John Moore. And in these cases, we're injecting kind of, lower than the standard SAI, because we're in these polar regions or subpolar regions where the tropopause is lower. That's what this figure is showing here. But there'll be some new model simulations coming out of the GeoMIP experiment, G6 1.5K Hiller. So hopefully there'll be plenty of new data for the community to analyze around these low altitude injection scenarios. Cool, I'll stop there and take any questions.
Okay, Sean first.
Alistair, thank you ever so much. Great talk. So I know the modeling has been for SAI, but given what you've described regarding differential areas, can you postulate, if you haven't looked at this, whether if you were to combine a more localized approach, and I'm thinking something like Arctic sea ice thickening, preserving a greater albedo over the Arctic in the summer with SAI, how might that A, affect the results, and B, suggestions as to where you would then find optimal location for SAI?
Yeah, it's a good question. I don't think I have a great answer to it. I guess I don't really know. I think what I get excited about with sea ice thickening is these near-term local benefits for people, fundamentally. That's what I think I really get excited about with sea ice thickening. And I guess for me, these pan-Arctic sea ice thickening ideas are less plausibly near-term. And I guess a lot of the focus on these kind of low altitude or polar SAI strategies are really thinking about the next few decades. Yeah.
Thank you for an excellent talk. Is it possible in the presentations on the Arctic and the high latitude analysis to break it down, perhaps part of that question, into the key components of Arctic climate? Because to make them visible would then make it clear what the benefits of intervention are or aren't. So sea ice, the glaciers, the ice sheet, snow cover, permafrost,
Yeah.
So there were little boxes, or anyway, as a sort of additional analysis.
Yeah, I think it's a good idea. I think that is something the community needs to do, actually. It'd be great to do that kind of full analysis across lots of the key indicators of Arctic climate. I'd love to get involved with that, definitely.
Jeff, University of Manchester. Slightly following on from Sean's point, and I've done a bit of work on this. It'd be nice to find out if your model has it. So you can have two effects, like you're doing a surface albedo, and you guys are coming and doing stuff above. The trouble is there, you get multiple bounces, basically create a mini greenhouse effect there. And they can really offset, particularly when you have a high albedo ground surface. So does this account for that extra bouncing?
Does this account for if you were to do sea ice thickening and get that extra bouncing?
Yeah, well, it's still there anyway, obviously, but you've got multiple reflections, obviously, from the surface.
Yeah.
Going up, hitting the sulfur side, and coming straight back down again where you don't want it.
Yeah, so that would be in the Earth system model. Certainly, the radiative transfer model would have the possibility to do that, right? But we're not doing any sea ice thickening in these experiments, if that's your question.
But but those two effects, we do them at the same time, they can cancel each other out slightly. So you'll be really careful if you're having multiple approaches at the same time.
Yeah, I think that's a good point.
I'm going to throw it to you, but there's no one.
Yeah, thank you for your presentation. And my name is Julius, and I'm from Sami Council. I really like the policy relevant figure that you had in your presentation, and on the I can't remember the exact details, but it was the amount of sulfates in grams, and was it the altitude too? Yeah, injection latitude. Yeah, what do you think is the factors that should be optimized here, and for policy makers to think about, or maybe, I don't know, I'm still trying to figure out my question, but what factors do you think are to be optimized? Should we minimize the amount of SO2 injection or in regards to injection latitude, or what do you think are the important things to optimize?
Yeah, it's a really good question. I would say that this metric is not a good metric for making policy decisions, right? Like it's one metric, but it's certainly not anywhere near the best metric. The reason I have put it there is because, in a way, the amount of stuff you put in the atmosphere is a reasonably good first-order proxy for many side effects. Right, acid rain, for example, is pretty much in total proportional to how much stuff you put up there, but it's not a good proxy for impacts more broadly. And ultimately, the community would need to do that full risk analysis of impacts across these different strategies to get close to answering that question, right? And that's a much more difficult task than doing this, which is what I did. Right?
Yeah. Thank you.
Time for one last. I'm not going to forget that.
Jacob from Centre Climate. So I'm wondering, why does the cooling not stay within the Arctic, but we see Arctic ramification and the warming is remaining in the Arctic? What's the difference there?
Can you say the question one more time for me?
So we've obviously got Arctic amplification in the Arctic. The Arctic is warming much more quickly than the rest of the globe.
Yeah.
Why is the cooling staying less constrained within the Arctic? Because you're saying that it cooling in the Arctic doesn't stay in the Arctic, but the warming is more staying in the Arctic.
Yeah, I guess that's kind of your question, is sort of why are these blue points all below the gray line, essentially, right?
Yeah.
And I think it's a really good question. Fundamentally, the different type of forcing, right? Like the greenhouse gas forcing is fundamentally different to a solar dimming, and it may just be that in these cases you're still not getting as much local SRM forcing in the annual mean as the greenhouse gas forcing in the Arctic, potentially. But I think it's quite a complex answer that I don't have a good answer to in total, right? There's lots of contributions to Arctic amplification. There's a big community debate about exactly what causes Arctic amplification, why it peaks in the winter. That's kind of an ongoing research effort, and it's certainly not a simple answer.
Fair enough.